Imagine that we were able to control space, or control time. The kinds of things that we'd be able to do would be amazing. I might be able to go from here to here, to here, to here, and over to here in only an instant. Now, we all think that this kind of trip would be impossible, and it probably is. But in the last few years, our ideas about the true nature of space and time have been going through some changes, and things that used to seem like science fiction are looking not so far-fetched. It's all thanks to a revolution in physics called string theory, which is offering a whole new perspective on the inner workings of the universe.
String theory holds out the promise that we can really understand questions of why the universe is the way it is at the most fundamental level.
String theory is really the Wild West of physics.
This is an area of theoretical physics which is so radically different from anything that's been before.
This radical new theory starts with a simple premise that everything in the universe, the Earth, these buildings, even forces like gravity and electricity, are made up of incredibly tiny, vibrating strands of energy called strings. And small as they are, strings are changing everything we thought we knew about the universe, especially our ideas about the nature of space. To see how, let's first shrink all of space to a more manageable size. Imagine that the whole universe consisted of nothing more than my hometown, Manhattan. So now, just one borough of New York City makes up the entire fabric of space. And just for kicks, let's also imagine that I'm the CEO of a large corporation with offices on Wall Street. Because time is money, I need to find the quickest route from my apartment here in Upper Manhattan to my offices in Lower Manhattan. Now, we all know that the shortest distance between 2 points is a straight line. But even if there's no traffic, a bit of a stretch, even in our imaginary Manhattan, it'll still take us some amount of time to get there. By going faster and faster, we can reduce the travel time. But because nothing can go faster than the speed of light, there's a definite limit to how much time we can cut from our journey. This Manhattan universe fits with an old classical vision of space. Basically, a flat grid that's static and unchanging. But when Albert Einstein looked at the fabric of space, he saw something completely different. He said that space wasn't static. It could warp and stretch. And there could even be unusual structures of space, called wormholes. A wormhole is a bridge or a tunnel that can link distant regions of space. In effect, a cosmic shortcut. In this kind of universe, my commute would be a New Yorker's dream. But there's a hitch. To create a wormhole, you've got to rip or tear a hole in the fabric of space. But can the fabric of space really rip? Can this first step toward forming a wormhole actually happen? Well, you can't answer these questions on an empty stomach. Turns out that by looking at my breakfast, coffee and a donut, we can get a pretty good sense of what string theory says about whether the fabric of space can tear. Imagine that space is shaped like this donut. You might think that it would be very different from a region of space shaped like this coffee cup. But there's a precise sense in which the shape of the donut and the coffee cup are actually the same, just a little disguised. You see, they both have one hole. In the donut, it's in the middle, and in the coffee cup, it's in the handle. That means we can change the donut into the shape of a coffee cup and back again without having to rip or tear the dough at all. Okay, but suppose you want to change the shape of this donut into a very different shape, a shape with no holes. The only way to do that is to tear the donut like this, and then reshape it. Unfortunately, according to Einstein's laws, this is impossible. They say that space can stretch and warp, but it cannot rip. Wormholes might exist somewhere fully formed, but you could not rip space to create a new one over Manhattan or anywhere else. In other words, I can't take a wormhole to work. But now, string theory is giving us a whole new perspective on space, and it's showing us that Einstein wasn't always right. To see how, let's take a much closer look at the spatial fabric. If we could shrink down to about 1/millionth of a billionth of our normal size, we'd enter the world of quantum mechanics. The laws that control how atoms behave. It's the world of light and electricity and everything else that operates at the smallest of scales. Here, the fabric of space is random and chaotic. Rips and tears might be commonplace. But if they were, what would stop a rip in the fabric of space from creating a cosmic catastrophe?